Okay, so it's my pleasure to introduce our speaker for the afternoon, Cheuk Yu Mak from Cambridge. And he's going to be telling us about symplectic annular Khovanov homology. So take it away.
Yeah, thank you. Thank you very much. Thank you for the introduction. And thank you for the invitation. So let me share my screen first. Okay. Can everyone see it and hear me? Is it okay with my voice? Yeah, that's good. So, right. Today I want to talk about symplectic annular Khovanov homology. It is based on a joint work with Smith. The talk consists of three parts. The first part is about the symplectic Khovanov homology. Which was introduced by Siegel and Smith, and it is denoted by AH symplectic. And then I will move on to talk about the annular version, the symplectic annular Khovanov homology. So, and it is denoted by AKH sim. And finally, I will explain how to construct a spectral sequence from the symplectic and annular Khovanov homology to the symplectic Khovanov homology. And so let's move on to the first part. So the first part is symplectic Khovanov homology. And symplectic Khovanov homology is a length invariant. And how is it defined? So given a length, say k, then you can write the length as the closure of a braid. So closure of a braid. And beta is an element in the braid group. This is the braid group with n strands. And then, for example, if you take a simple braid in the braid group of 2 strands of this form, then your length, then the corresponding length as the braid closure of this braid is this one, which is the unknown. And different braid closures are related by a sequence of local Markov moves. So which identify so the moves are as follows. The first one says that if you conjugate your braid beta by an element sigma, then the resulting length are the same when you write them as braid closures. And the second move is if you compose your beta with a simple braid of this form, then then after taking braid closure, you will get the same braid closure as before, meaning that before taking the composition. So these two are the same. And what Seidel and Smith did is that they define length invariance as follows. So to each positive integer n, they consider a distinguished symplectic manifold Yn, a distinguished Lagrangian submanifold inside for L rainbow. And then they also consider a break group action on this Yn. And the invariant is simply defined, the symplectic Khovanov homology is simply defined as the Lagrangian flow cohomology between this distinguished Lagrangian and the beta-beta image of this distinguished Lagrangian. Beta-beta is the image of beta under this group action. And what they prove is that this is a Markov invariant, which means that it is a well-defined length invariant. And to explain it in more details, I need to explain what is the symplectic manifold, Lagrangian submanifold, and the break group action. 1, 2, 3. So let's start with the symplectic manifold. So to construct the symplectic manifold Yn, we first need to consider the A2n-1 lunar fiber, which is this hypersurface defined explicitly by this equation. And it has a Lipschitz privation to compress plane by projecting to the z coordinate. And the Yn is the Hilbert schemes of endpoints on this A2n-1 lunar fiber deleted by a divisor, a complement of a divisor in the Hilbert scheme. And the divisor is the closure of some space. So Hilbert schemes is a resolution of a symmetric product. So most of the points in Hilbert schemes can be regarded as unordered n-tuples of points in the lunar fiber. And the divisor is all the unordered n-tuples of distinct points, x1 up to xn, such that the cardinality of the projection of this set is strictly less than n. And the pi here is the pi here is this pi. And this is an exact symplectic manifold. So the Lagrangian flow cohomology can be easily defined. And then I need to explain what is the distinguished Lagrangian submanifold. To define it, we introduce this picture. So this is the standard. This is the base of the Lipschitz privation with critical values 1 up to 2n. And then we consider the matching path, the matching spheres lying above L1 up to Ln. And the distinguished Lagrangian L wingle is the product, consists of the n-tuples x1 up to xn such that xi belongs to Li, so is the product. And then you forget the ordering. And I claim that it lies inside Yn. It is away from the divisor D. And as you can see, so if you trace back the definition, you can see that it lies inside Yn. And in general, for any collection of n pairwise disjoint Lagrangians, any collection of n pairwise disjoint Lagrangian, L1 to Ln, we can define a Lagrangian in Yn in the same way, and it will be denoted by sim L. Any question? And then I need to explain the break group action. So the Bray group action comes from varying the critical values of this ulnar fiber. And so by varying the critical value, you see that this fundamental group acts on the ulnar fiber, and this is exactly the Bray group, but with two end strands. And we claim that by similar reason, it also acts on, this group also acts on the yn, because yn is the complement of the Hilbert, a complement of a divisor in the Hilbert. And in particular, we can consider a subgroup inside the Bray group of two end strands, which is we consider the subgroup of the left end strand. And this group acts on the symplectic manifold yn. So for example, if we consider the simple Bray, then the action of this Bray to the distinguished Lagrangian is given by this picture. So, arrow rainbow is this one. And then after applying the twist, then it becomes like after applying the twist, then it becomes like you rotate the left 2 points. And in summary, the symplectic Khovanov homology is defined by this form, the Lagrangian Fourier homology of the distinguished Lagrangian L rainbow and the phi beta image of L rainbow. So for example, if we consider this one, then the beta is this guy. And the Fourier homology, the symplectic Khovanov homology is the Fourier homology of the red guy and the green one, of the red one and the green one. The red one is L rainbow, and the green one is phi beta L rainbow. Any questions so far? So this is a the symplectic Khovanov homology, and then a recent theorem of Abouzaid and Smith, they proved that in characteristic 0, the symplectic Khovanov homology is isomorphic to the Khovanov homology, the ordinary Khovanov homology defined using combinatorics. And now, if no question, then I will move on to the annular symplectic Khovanov homology. Okay. So, similar to the symplectic Khovanov homology, to define the annular symplectic annular Khovanov homology, we need the data of the symplectic manifold, Lagrangian submanifold, and also the data of the Bray. And for the symplectic manifold, what we are going to use is two sequences of spaces. I mean, indexed by two integers. It is the Hilbert scheme of endpoint on AM-1 Müller fiber, deleted by the corresponding divisor defined analogously. So in particular, yn to n is the yn previously. And this guy has a map to the complex number by taking the sum of the Lipschitz privation pi. we talked about before. So sum over n I equals 1. And and then we need the data of Lagrangian submanifold. So what we are going to use is we will use sim L. So this means this is the previous construction. So you take the product. So L is a collection of n pairwise disjoint Lagrangians. You take the product of them and then you forget the ordering. And we need each Li to be either compact or a symbol of the AM lunar fiber with respect to the Lipschitz privation pi. So for example, so if we define this is L1, this is L2, we have a collection of two pairwise disjoint Lagrangians. And then the corresponding sim L will define a Lagrangian inside Y24. And for this Lagrange, and we are going to consider these Lagrangians as our objects in the corresponding Fukaya-Seidel category. So, and we are going to denote the Fukaya-Seidel category with respect to this map, the map above. We will denote this category by FSYNM. And to illustrate the wrapping of this category, let me say, for example, if we consider this is my L, and this is my K, the home between these two is defined to be, you wrap the first one. Maybe I should use a different color. Here. And then you wrap the first one to the right. This is K. So after taking sim, you will see that this picture means that they don't have intersection. So in particular, the home space is 0. And then for this Fukaya-Seidel category, so it is again generated by Lagrangian symbols. And the Lagrangian symbols, we claim that they are simply the products of symbols. Where L is a collection of symbols. And this is a generalization of an observation by Auroux. So in a previous work by Denis Auroux, you observe that for all, if you replace the Milnor fiber by an open Riemann surface, then the corresponding co-core will, the product of the corresponding co-core will split generate the split. Anyway, will split generate the Fukaya, the corresponding partially wrapped Fukaya category. And then, so but this is quite funny in this case, because it would directly mean that the Fukaya-Seidel category, or maybe not very fun, maybe it actually directly implies that the Fukaya-Seidel category is 0 if n is greater than m. Because when n is greater than m, you cannot find n many pairwise disjoint Lagrangian symbols. These are pairwise disjoint. And it is generated by a single symbol if n equals to m. And so I should remark that there are two remarks I should make. The first one is that this guy is not, maybe this is a remark to expert. So this guy is not a nilpotent slice when 2n is greater than m. So that's why it can be 0. And the second remark is, in this case, to an expert of another group of experts, which is, so when n equals to m, the setting is quite similar to the higher dimensional Higa-4 theory defined by Colin, Honda, and Ken. But I want to say that the wrapping defining the Lagrangian floor theory here is different from the higher dimensional Higa-4. By Colin, Honda, and Yen. So if you right. So, but these two remarks are not related to what I'm going to talk about next. So if you don't know what if you don't understand this remark, it doesn't matter. And then for this Fukaya-Seidel category, we show that in characteristic 0, as in the results in Abouzaid, this Fukaya-Seidel category of YNM is the same as the category of perfect modules over KNM, where KNM are some say graded algebra. They are called the extended algebra, defined by Brunden and Stropel. which is a generalization of the algebra defined by Khovanov. Any questions so far about the category or about the theorem or about the setting? I don't know in characteristic P. So yeah, that's a good question. But the method doesn't apply in characteristic P. So I don't know. And if no further question, then let me continue. So actually from this Cauchy equivalence, one can deduce that the Fukaya-Seidel category of YNM is the same as is Cauchy equivalent to the Fukaya-Seidel category of Ym minus Nm, and it is the same as the Fukaya-Seidel category of Ym minus Nm. There is a duality between the Fukaya-Seidel category. And this is not merely just a consequence of the Cauchy equivalence above. And in fact, we can realize them geometrically. And we will come to this point later. So I haven't finished introducing the symplectic annular Khovanov homology because I haven't said anything about the braid. Remember that I said that we need the data of a symplectic manifold, Lagrangian submanifolds, and also the data of braid. The data of braid is similar. So we have a braid group action from the braid group of M strands to YMM by similar reason. And it also it will goes to, so if you ignore what happens at infinity for the, if you forget about the technical difficulty at the infinity for the moment, then you will expect that it sends to the bimodule over the Fukaya-Seidel category of YNM. This is my notation for bimodule. And it is, so the beta, if you give me a braid, it will send all the way to a bimodule over this Fukaya-Seidel category of YNM. And now we have everything we need to define the symplectic annular Khovanov homology. And definition. The symplectic annular Khovanov homology of the braid is defined as the direct sum of partial homology of the Fukaya-Seidel category FSYNM with coefficient in the bimodule M beta n. So at first, you might think that this definition is quite unnatural. And so, but if you one thing that I don't know whether it helps or not is that you might think of this as a fixed point floor homology. Regard it as certain fixed point floor of phi beta. And then this direct sum is like if you regard the YNMs as a symmetric product, although they are not symmetric products, but they are kind of closely related to symmetric product. So then this direct sum is taking the direct sum of the fixed point floor of some symplectomorphism with respect to all symmetric product. So it looks vaguely similar to the periodic floor homology in some sense. Is it? I cannot read. What was the question? E?
So it's easier to compute than fixed point floor homology. Like, why are you using Hochschild homology? Why you are using it?
Why am I using it? Because you will see that it is it will be closer related to the ordinary annular Khovanov homology. That I'm going to say now. So right. So
You don't have a general way of computing using this extended arc algebras like an algebraic way, or
say it again. I cannot hear you very clearly.
sorry, you don't have a I don't know, like a general way of computing this in terms of this extended arc algebra. I don't know.
So I compute the only way that I know how to compute this is using the extended algebra, but then it is a difficult algebraic problem. In general, for different states. Did I answer your question?
Sure, okay, thanks.
Right. So as a continuation of our previous theorem, so we show that in characteristic 0, this guy is isomorphic to the annular Khovanov homology defined by Ashta, Rezchikov, and Shikura. So in particular, it is a annular length invariant. Actually, you can already see that it is an annular length invariant because it is a direct sum of partial homology. So, but in particular, they are isomorphic as annular length invariant. Annular length invariant, for which I mean, so you have your beta, and then you can take the break closure. But now you regard it as a length inside the solid torus. And at this point, I want to mention several historical remarks. The first one is that when n equals to 1, so for y1m, which is am minus 1, the Müller fiber itself. So it was proved by Auroux, Grisby, and Rayleigh. It's proved by them that the Hochschild homology of the Fukaya-Seidel category with the corresponding bimodule is a direct summand of the annular Khovanov homology. So this is the first piece, or maybe the second piece of this. So the first piece is n equals 0. It's the trivial piece. And then secondly, motivated by their result, Syegel, Futura, and Rayleigh, they show that the annular Khovanov homology can be written as the direct sum of Hochschild homology over of the extended R algebra. So and finally, our contribution is that we apply the idea in the proof of symplectic Khovanov equal Khovanov. Apply the idea in Abouzaid-Smith to this case to show that the symplectic version of annular Khovanov is the same as annular Khovanov. So most of the proof in this theorem is to setting up the correct framework to deal with what happens at infinity. And so I don't want to explain this proof in this talk, but instead I want to say something else. So instead, I want to explain how to use this symplectic annular Khovanov homology to get a spectral to get a spectral sequence to the symplectic Khovanov homology. First, I need to first say that there exists no construction of a spectral sequence from the annular Khovanov homology to the Khovanov homology using the combinatoric definition of AKH. And it was not clear how to get the spectral sequence using the direct sum of HH definition of AKH. But I will illustrate that this spectral sequence comes very naturally from from this geometric point of view. Any questions so far? So let's recall this symplectic annular Khovanov homology is the sum of the Hochschild homology with coefficient in the bimodule m beta n. And then on the other hand, this guy is the same as the Lagrangian flow cohomology of this guy and between this guy and that guy. And then we want to get a spectral sequence between the two, from one to another to the other. So one thing to note is that on the left-hand side, the flow theory is happening inside Y and M, where n is from 0 to n. And on the right-hand side, the flow theory is happening in Ym to M. So the first question is, how are the two related? And the answer is surprisingly simple. They're related by the fact that an M tuple is the union of an N tuple and an M minus N tuple. It means that we can define a functor for each N. We can define a functor from the Fukaya-Seidel category of Ym cross Fukaya-Seidel category of Ym minus Nm to the Fukaya-Seidel category of Ym to M. It is simply given by, for example, like this. And then it is simply given by stacking the diagram. It is not hard to convince yourself that this guy is a cohomologically full and faithful embedding. Fully faithful. Because the flow theory, they look the same if you just look at the picture. But there's another thing which is also nice, also not very deep, but maybe a little bit harder to see, is that we actually have a semi-orthogonal decomposition. Of Ys, Fsym to M. Being the essential image of this embedding. The reason why we have such a directness between the essential image is very simple. So for example, if we consider so L, which is lying inside the essential image of I3, and we consider another Lagrangian, say like this. Okay, which lies inside I2. So the subscript correspond to how many Lagrangian you have on the left. So we have 3 blue and 2 green. And then right. And then after wrapping, you can see that the home KL is 0 because we are wrapping the first factor to the right. So it's quite obvious. So it's obvious why we have this directness. And and the generation. Sorry, I cannot see the question. It jumps and then I.
Sorry. So question is, can you say again? I'm getting very confused now. I thought that IN was a functor from a product of 2 Foucault-Seidel categories, and I didn't see the difference between the 2 sides.
The difference between the 2 sides.
I mean,
so here the subscript is n. Here the subscript is y minus n, and then maybe the color is confusing. So so the L is the image of this guy I3, and the K is the image of this one. So this is inside Fs Y23. This is inside Fs Y13. Does it make some sense?
I think I had missed some details about what Y and M was, but now I get it. Thank you.
Okay, that's great. Any more questions? Great. So, right. And then, see. And it is a good time to recall that we have the Foucault-Seidel category of YNM is closely equivalent to the Foucault-Seidel category of Yn minus NM. So, so the domain category of the functor is actually a bimodule. You can think of this as a category of bimodule. So, now the proposition is we can consider left module and then pull back by this fully faithful embedding to this Fs YNM cross Fs Ym minus NM module. But then it is the same as the bimodule over YNM. And the claim is that it sends the left Unida embedding of this distinguished Lagrangian to the diagonal bimodule over this Foucault-Seidel category. Let me explain why using pictures, but not an actual proof. So at the left Unida embedding of this distinguished Lagrangian is like this. This is the L rainbow, and then You need to, after taking pullback along this IN, it corresponds to you put some object in the Fukaya-Saito category of YMM here, YNM here. And then you put another object of YN minus M minus N, M here. And I claim that you can slide it. After sliding, so it will become upside down. And then I claim that this whole thing is exactly the geometric map relating the two. So let me give an example. So if I consider this picture, so the blue one is inside Y13, and the green one is lying inside Y23. Y1. And then you take the home L rainbow, L union, okay. And then it is the same as, so you slide the picture to the top, and then you shrink all the black, and it becomes like something like this. L E of D. Where the D here is the geometric map relating the two categories. And can you see? The screen share seems a little bit strange. Can you hear me? Ah, okay, it works now. So what you do here is, so yeah, so this is the so-called sliding procedure. So in particular, it means that the left uniter embedding of this L rainbow has I mean the components of this guy with respect to the semi-orthogonal decomposition, all of them are diagonal bimodal. So the left uniter embedding of L rainbow can be built from iterated form of the diagonal bimodules. Any question so far?
Yes, Cheuk Yu, can you explain again how the map D works? How did you go from having two green arcs to just one?
So the actual proof is by explicitly constructing train map relating the two. So So for example, here we only have one intersection point. It means that whatever we get is something tensor by a k, and then we can remove this guy. And then for the other, for shrinking the black and the green to a single one, we do something similar. So the actual proof is not really just erasing. You are really constructing a string map relating the corresponding string groups. But it is not very difficult because they don't have complicated intersection patterns. They are basically quite disjoint. They only intersect at the critical point. And then let's move on. Right. And then we need one more input to deduce the spectral sequence, which is we need to consider the Kossuth-Diel semi-orthogonal decomposition. So it means that we need to consider another sequence of embeddings, FSYNM cross FSYM minus NM going to FSYM to M. This time, we kind of want to use some upper half matching in some sense, and then it maps to something like this. So basically you put everything. You put the green region here. And then the claim is again that the claim is similar. So Jn is fully faithful. And then we also have the corresponding semi-orthogonal decomposition. And the proposition is similar. The proposition says that the right Yonader embedding of this guy will send to the diagonal bimodule. So the difference between the left and the right has something to do with the wrapping that I chose. So that's why there is a discrepancy between the left and the right. So and this semi-orthogonal decomposition, is the Kossuth-Diel in the appropriate sense, meaning that and which is very similar to the usual Lipschitz vibration situation, Fukaya cycle for Lipschitz vibration. And then the consequence is that we have a Bayesian type spectral sequence. From the direct sum of what? Of the right of this one, wrinkle, and then tensor over bimodule. Y and M, and then you put I here. YL. J Y to the home of L Wingbo. And this guy is exactly the Hochschild homology. And for the results in general, you just need to apply the twisting, the break group action on both of these two factors. Then you will get the corresponding results for general brain. And this is the end of my talk. Thank you very much.
Okay, so let's thank the speaker. Are there any questions? So I was wondering, sorry. First, I guess Mohammed has a question. Mohammed, do you want to go ahead, or we can read it, I guess, in the chat?
Sure. I mean, I think my question was clear. I mean, you mentioned that somehow this wrapping is different. I didn't understand this relationship with this higher dimensional Hager-Fleur that.
Right. The higher dimensional Hager-Fleur, the wrapping is infinitesimally wrapped in the sense that we don't wrap the brewer. We don't go all the way to the right. It's really infinitesimal. So this one, right? So here.
Sorry, what you don't. Sorry, I'm confused. In your work with Ivan, you do something infinitesimal?
We do something with respect to. So we do, yes, is with respect to a stop, but the stop is so. Let me say, let me draw the example. So, in what we do is that we wrap like this, and then but in the case of the higher dimensional Hager-Fleur, what they do is they wrap like this. This is how.
I see, I understand. You're saying theirs is more infinitesimal. Okay, I understand.
Right.
Thanks.
Yeah, thank you for the question. And do you have a question, Tyler?
Yeah, I guess I was just wondering, like, is there, would there be any value in like mimicking this construction with, replacing AN Milner fiber with like DN or something? And
Yeah.
Also, should I think that like this Fukaya-Saito category of like YNM or its analogs can somehow be recovered by some categorical information of the original manifold, like AN in this case?
Right. So for your first question, yes. So you can consider the DN Mueller fiber, but instead you will have another break group action. So yeah, you can guess it's the type D break group. So and then you can do the similar things, but it will be not very natural in the if you want to define a link invariant, it will not be very natural because you don't know which group which AN or yeah, of course type A and then into type B, but then it is not very helpful to have such a theory. So and for your second question, so whether it can be recovered from the information from AM Mueller fiber, and my guess is that if you consider higher genus information, I mean not necessarily higher genus, but I mean just yeah. I mean, if you consider more holomorphic curves in the AM Mueller fibers, then you can recover this theory of the Fukaya category in YN. You in general you need to look at just like in Higa-Froh, you need to look at some branch covering to the disk, and then a map, holomorphic map from the branch cover to your AM Mueller fiber. Did I answer your question?
I see. Yeah, I think so. So I could think of this as sort of like I could almost think of it like a higher genus invariant of AN, or
right. Yeah, you can. Yeah, not necessarily higher genus, maybe also genus 0, but more complicated curves. But yeah, it also captures some information of higher genus. Yeah. That's right.
thank you. So Semen Rezchikov also has a question. Do you want to unmute yourself? Or?
Yeah, sure. So you, in your abstract, you also mentioned that, I guess, because you show that these things are equivalent to these categories are equivalent to representations of this associative algebra, this shows that these Fukaya categories give like symplectic incarnations of certain, I guess, parabolic blocks of category O for SLN. So my understanding is this is supposed to fit into like a more general set of ideas about how to realize these types of categories, these sort of representation theoretic categories using Milnor fibers. Do you have any like comments on how to think about that, or from your perspective, and also like any potential further kind of problems with trying to generalize your work in that direction, and or potential viable paths forward?
I've thought about this question for some time, but I think to me, I think it is quite difficult to do it using symplectic method. So I don't have a good answer to your question. Sorry.
Okay, thanks.
Yeah.
So any other questions for the speaker? Okay, so I'll go ahead and stop the recording, and then people should feel free to stick around.
This video.
What's that?
If you like this video, you can subscribe.
If you like this video, please subscribe. Yeah. So people can feel free to stick around for a more informal discussion. So, but first, let's thank the speaker one more time. Thanks again.
Thank you. Thank you for coming.